in this first session today. Noah, I see you there. Hi.
Oh.
Can you hear me?
Yes, I can.
Oh,
Can
there
you
you
hear
are.
me?
Great. Yep, great. So go ahead and share your screen. Make sure it works. Yep, I can see it. Go ahead and go full screen. Our next speaker is Noah Kleeke from University of Michigan, who just finished his master's, so he'll be starting his PhD with us in the fall. And he's going to talk today about genetic algorithm optimization of shielding for plutonium safeguards measurements. So Noah, please go ahead.
Awesome, thank you. One of the most serious dangers in the world today is the threat from nuclear weapons. In 1953, President Eisenhower gave his Atoms for Peace speech to promote the peaceful uses of nuclear material and technology. Today, there are treaties between countries, such as the Nuclear Non-Proliferation Treaty, to establish guidelines and nuclear safeguards for nuclear weapon and non-nuclear weapon state parties. Nuclear safeguards are used to control special nuclear material, such as plutonium, and are quintessential to global security and safety. Recently, more interest has been shown in using organic scintillators for safeguards measurements, as opposed to the current state-of-the-art helium-3 detectors, because they do not need to use moderation for neutrons to improve detection efficiency, and they are also sensitive to both neutrons and photons. Last summer, there was a planned measurement by the Detection for Nuclear Non-Proliferation Group at the University of Michigan of beryllium-reflected alpha-phase weapons-grade plutonium. Now that's a mouthful to say, so it's just called the burp ball. This measurement was going to be taking place at NSERC, the National Criticality Experiments Research Center, within the device assembly facility. And that's in the Nevada National Security Site. On the middle right here, you'll see a diagram of the main components of the burp ball. And on the far right, you'll see a table with approximate weight percentages of specific isotopes in the burp ball. These weight percentages were taken from the actual information of the fabrication of the burp ball in 1980. So they're a little bit older, but as you can see at the bottom of the table, there is a buildup of americium-241 in the burp ball. We planned on using trans-stilbene organic scintillators for this measurement, and it is known that organic scintillators experience specific limitations of data throughput and pulse pileup because of when measuring plutonium samples because of the buildup of americium-241. Americium-241 decays to neptunium-237, emitting 60 keV gamma rays with a high specific activity. So in summary for this work, we needed to somehow shield the lower energy non-fission gamma rays, predominantly from americium-241, while minimizing the intensity loss of the higher energy fission gamma rays and neutrons that we were trying to measure. We came up with a solution of placing tin and copper sheets in front of the detection system. Tin and copper were used because they have very high mass attenuation coefficients for low energy photons. These materials are less effective at shielding higher energy photons. The area of the front face of the detection system was known prior to the measurement. However, the actual material, the shielding material thicknesses were not known and thus needed to be optimally selected. So in this work, we used a genetic algorithm to perform that optimal selection. Genetic algorithms are robust, meaning they're both efficacious and efficient. These algorithms search in a sample space using random choice, but in a directed search process. On the bottom of the slide, I give a side-by-side comparison of how long a brute force search method would take in comparison to how long our genetic algorithm took. And you can see that the total time difference is pretty substantial. In summary, for the last couple slides, the main two goals that we had for this project were to design the tin copper graded shielding to shield the low energy gamma rays, particularly those from americium-241, while still being able to detect the fission neutrons and photons. And then number two is to demonstrate the efficacy of genetic algorithms in multivariate shielding optimization. So this diagram illustrates the way our genetic algorithm worked. First, the user would input certain parameters before the genetic algorithm actually started. And after these input parameters were specified, the genetic algorithm launched into action by setting up the sample space and then breaking that sample space into equal components. And after dividing the sample space into equal components, would randomly sample in each of those components. This method was known as the Latin hypercube sampling method. And based on those random samples, the genetic algorithm would actually write MC&PX Polymia input files for simulation. The next step would be to construct a batch file to run each simulation sequentially. And then when all of those simulations are done running, we collect the output data from MP-Post, which is a post-processing script. Based on that data, we used a figure of merit to judge how well the shielding designs performed, or how, like, quote unquote fit they were based on this figure of merit or objective function. And then step 5 would be crossing over the chromosomes of the population. The chromosomes in this case would contain the information pertaining to the shielding material thicknesses. So once we cross over those chromosomes, you actually get genetic information from both or two parents, where one of the parents is preferentially selected because it has a very high figure of merit or fitness. Now, the user initially specifies the number of generations of populations. And if the genetic algorithm sees that there's another population to be produced, it goes back to step 1 and skips the Latin hypercube sampling method because you already have that new population from crossover. And I forgot to mention, we also add a mutation rate so that the entire the sample space is searched. But if the generation index isn't exceeded, it goes back to step 1 and performs basically the step 1 through 5 again. But if the final population was produced, the genetic algorithm outputs the final solution, which also had a list of the best performing shielding designs. A simulation template was designed for the genetic algorithm. Two variations of this template were used, one with a beam source of 60 keV gamma rays from americium-241, and the second one, a beam source of spontaneous fission photons from plutonium-240. On the right, you'll see the array of trans-stilbene organic scintillators coupled to PMTs behind the graded shielding of tin and copper. So the animation on the left side of the screen here shows the genetic algorithm actually working. Each screenshot is taken every 10 generations, and the plot on the right shows the final output from the genetic algorithm. Now, for each of the genetic algorithm runs that we did, we had a population size of 36, a mutation rate of around 16.7%, and 50 generations. The animation that I mentioned before, it'll pop up again, but it shows that initial Latin hypercube sampling method followed by the convergence to the solution in the bottom left corner. The color bar on the right side is actually the figure of merit, and we want this figure of merit to be as high as possible, so we want it to be as dark red as possible. The figure of merit, abbreviated FOM, is shown here below the animation and the figure. So when we were coming up with this figure of merit, we wanted to maximize the number of plutonium-240 detections and minimize the number of americium-241 detections. The number of detections is abbreviated or denoted with a little n. We also took into account the total number of particles simulated for both the plutonium-240 input files and the americium-241 input files. And you'll see here it's abbreviated capital NPS. Now, you'll also see in the figure of merit that there's a constant, that's 0.01, that's in red. We use that so if the number of americium-241 detections was 0, our figure of merit wouldn't skyrocket to infinity. Now, the constant that I mentioned before, that red 0.01, was changed multiple times. In this slide, you'll see that the constant was changed 3 times. And what we actually call that constant is the americium-241 attenuation weighting factor, because as the weighting factor decreases, the importance of the americium-241 detections increases. The plots above show that when you decrease that weighting factor, the optimal shielding design has actually a greater distinction with regard to the figure of merit. The americium-241 attenuation weighting factor, that red C in the figure of merit, which I was talking about before, was changed a total of 12 times. And the plot on the left, you'll see material thickness plotted as a function of that weighting factor. And as the weighting factor decreases, the material thicknesses for tin and copper asymptotically approach 0.12 centimeters and 0.15 centimeters respectively. When the optimal thicknesses do not change by more than 0.02 centimeters or 17% when the weighting factor is less than 10 to the negative 4. On the right, you'll see the ratio of copper thickness to tin thickness plotted as a function of that weighting factor. And as the weighting factor is decreased, the ratio actually asymptotically approaches 1.25. Now onto the actual experiment. One of the optimal shielding designs was used to purchase the tin copper graded shielding. You'll see the manila folder. The shielding is actually in those manila folders, which is placed in front of an array of 12 transtylvene organic scintillators. There were 3 sources that were measured: californium-252, which is shown here on the left, the Burpal, which is shown on the right, and then AMLI, which was measured in the same configuration as californium-252. 2 helium-3 based detection systems were also present during the experiment, but their data is not used in this work. A pole-shaped discrimination plot was created for the measurement of the AMLI source, which is shown in the slide. The smearing of the 2 distinct peaks or bands, for neutrons and gamma rays, you can see in the left plot is from pulse pileup. You'll notice in the second figure on the right that with the implementation of the tin copper graded shielding, the noise and the high tail to total integral ratio values were reduced. The count rate of gamma rays emitted by the californium-252 source was measured as a function of energy deposition. The count rate significantly decreases when the californium-252 source was measured with the shielding, as you can see on the left. The large difference in bare count rate versus shielded count rate at low energy deposition, and the small difference between bare count rate and shielded count rate at larger energy deposition demonstrates that the shield actually preferentially shielded the lower energy gamma rays, which we wanted. The same effect is shown here on the right with the ratio of bare to shielded counts plotted as a function of energy deposition. You'll see the ratio spike at low energy deposition and then level off at higher energy deposition. In total, for this work, we have demonstrated that genetic algorithms can successfully be implemented in nuclear engineering applications. The resultant reduced gamma ray flux will allow detection systems to be placed closer to plutonium sources in the future. therein increasing detection efficiency. And lastly, improved efficiency offers many advantages, including better measurement time or better measurement precision and shorter required measurement times. In the future, we're looking to quantify the uncertainty of the genetic algorithm and test the genetic algorithm for other shielding applications. I'd lastly like to talk about how the MTV has had an impact on me personally. I've been able to attend multiple workshops and conferences and also make valuable connections at consortium events. I'm currently working as a student intern in the Los Alamos National Lab Advanced Nuclear Technology Group within the Nuclear Engineering and Non-Proliferation Division. And then I would like to acknowledge that this work would not have been possible without the support of the NNSA and the DOE. And with that, I'll take any questions you guys have.
Thanks, Noah. Excellent talk. I don't see any questions in the chat yet, so I will ask one while people think. And it's kind of a naive question, but I don't think you addressed it. Can you talk a little bit about the choice of tin and copper specifically? Why not other materials?
So I think I mentioned this a little bit earlier, but the mass attenuation coefficients for tin and copper, my mentor and I saw were very high for the energy that we're trying to shielding, that's 60 keV. And so we initially thought that tin would be great to shield those lower energy photons, but that tin also emits secondary X-rays that the copper would shield. So we're placing tin in front of copper, but we didn't know exactly how much material for like the material thickness for tin with copper there. And we didn't want to do this by hand, so we came up with the idea of the genetic algorithm to help us out.
Yeah, that makes sense. So the order matters. So the tin faces the source, the plutonium.
Yes.
Right. Okay, that makes sense. And you showed a nice result where you varied this factor you called C, and it was clear that, you know, especially at higher values of C, the ratio changed, right? The results changed. So I don't think you mentioned what exactly were the final thicknesses you decided on for the shield that were eventually deployed at the NSERC.
At
It levels
NSERC,
off there, but yeah, what were the thicknesses there?
Yeah, they were actually right around that 0.12 centimeters for tin and 0.15 for copper.
Mm-hmm.
I can't recall the exact thicknesses, but they weren't very far off from that ratio and those material thicknesses.
Okay, so this plateau with the lower values of C, you chose from kind of that plateau region, which makes sense.
Mm-hmm.
Do you remember what the total effective attenuation was for the 60 keV gammas with that final shield?
No, I did not calculate that.
Okay. Question from the chat is, do we plan on extending this to other applications such as Linux shielding, for example, where neutron measurements become of interest?
Yes, I was actually hoping to collaborate with a boss soon who's doing similar work with tin and copper shielding, and hopefully come up with something for optimizing his experiments as well.
Mm-hmm. Okay, great. I'll just ask if anyone in the audience has a question they want to speak up and answer. Please feel free to do that. If not, thank you, Noah, for a very nice talk.